Now children, today we are going to revise numericals of ray optics, and we will do this topic in two parts. We are going to understand and practice all important possible questions which can be there in your semester 2 exam paper. So before we start numerical, let us find the formula which we must remember. First, power of lens which converges the parallel rays, more is said to have more power. The lens which converges more has more power, and so the focal length of lens which is having more power is less in comparison to focal length of lens which is having large focal length. The power of this lens is less in comparison to this lens. Therefore, we will write that focal length of lens unit diopter is 1 upon focus if focal length is being substituted in meter, and 100 upon focus if focal length is substituted in centimeter. Then always remember that power of converging system is positive. If in some circumstances convex lens is behaving as concave lens, then its power will be negative. So power of converging system is positive. Power of diverging system is negative, and the rays should be paraxial in all the discussions we are going to do, and the lens should be thin. Then children, remember, always substitute focal length in the formula with sign. Effective power when two lenses are in contact will always be simply addition of power of first lens and power of second lens with sign. Here we need to remember that the medium in which both the lenses are placed on the two sides of the two lenses, the medium should be same. Then power of a mirror is -1 upon focal length, and the minus sign importance lies behind the fact that power of convex lens, power of converging system should be positive, but here concave mirror is converging. So to keep the power of concave mirror positive, we put power with -1 upon f. When we will place focal length of concave mirror with minus sign, the power of concave mirror will become positive. So therefore always remember, power of converging system is positive, power of diverging system is negative. So no matter which lens is behaving as diverging system, its power will be negative, and which lens is behaving as converging system, its power will be positive. Then we are going to use the formula n2 upon v minus n1 upon u is equal to n2 minus n1 upon r for the refraction from a spherical surface, single surface, where n2 is refractive index of the medium, refractive medium, and n1 is refractive index of the surrounding medium in which this refracting medium is placed. In this formula, always remember, you have to place u, v and r with sign. Then if we are talking about lens, that means we are having two refracting surfaces. Then from this formula, we derive formula of the lens, which is known as lens maker's formula, and 1 upon f is refractive index of lens divided by refractive index of surrounding medium minus 1 upon r1 minus 1 upon r2, where r1 is radius of curvature of first surface over which the incident ray incidence, and r2 is radius of curvature of that second refracting surface from where a refracted ray emerges. Then magnification of lens is v upon u, or size of image upon size of object, where v is distance of image from the optical center of the lens and u is distance of object from the optical center of the lens. So now after revising all the formula, we are ready to solve numericals. We can divide numerical of this topic in 4-5 parts. The first type of numerical which have been asked from this topic are refraction through single surface. This is question from 2003 paper and very important for this year. Use the formula for refraction through single surface, curved surface, and show that in this case u is equal to minus r upon n minus 1, where n2, that is the medium of the refraction, is n, and the surrounding medium is air, that is n1 is 1. So it's very simple. First you write a formula for refraction through single surface. Children, always remember, in board there is a specific pattern in which the marks are being allotted. The first thing which you need to do is write formula used. And the second thing you need to do is that show the substitution of values of different quantities in the formula you have written. So the first formula, write and put it in the box. After that, here N2, that the refracting medium is N, N1 is AR1, and in this case you can see that the ray after refraction is going at infinity. It is parallel to principal axis, so we will write the position of image is at infinity. Substituting the formula, simply the calculation will show us that U is the expression they are asking to prove. Although we have already discussed the important derivations of this topic, and all these important questions, derivations of semester 2 exam are together in playlist of the home page, that is semester 2 exam class 12 ISC. So you can go to home page, you can find this playlist, and you will have all the topics related to semester 2 exam which you need to revise at the last moment. But here I just want to recall that in 2 years lens maker's formula is being asked to derive, and this year also it is very, very important. Then in 2012 again a question is being asked from the refraction through single surface, and this question is saying that if radius of curvature of this spherical surface is 30 centimeter, refractive index of this medium is 1.5, this surrounding medium is air, then find position of the final image formed by the refraction through this surface. Very first thing, write the formula used. Then second thing, always remember, second step to represent your answer in your board exam is substitute. Show the substitution of values in the formula. So N2 is 1.5. V you want to calculate. N1 is 1. U, the rays are parallel, so object is at infinity. U is infinity. N2 minus N1 upon radius of curvature is plus 30. Because if you want to measure radius of curvature of this surface, then you need to move towards right, and the incident rays are also moving towards right. So all the distances measured in the direction of incident ray will be positive. Simple calculation will give you the position of image 90 centimeter, which is positive. Positive V means image is real and inverted. Then in 2004, the question is draw a diagram to show formation of real image through refraction of light at air glass spherical surface. And they have shown that you are having an object on the principal axis which is point object. So simply take two rays. After refraction, both the rays will bend towards the principal axis because of the nature of this refracting surface, and you will have a real image at some position on the principal axis itself. Then 2 years, this derivation is being asked, and this year also it is equally important. Handwritten notes of all the class 12 topics are being uploaded on my Telegram channel. Description box will have the link of my Telegram channel. Now come to this point. This is second type of question. Here we will have not single surface and refraction through single surface. We will have lens and two refracting surfaces. So 2001, a plano-convex lens has radius of curvature 10 cm. Its focal length is 80 cm and it is placed under water. Calculate refractive index of the material of this lens, where refractive index of the water is 4/3. Again the same step. First write the formula used. In air or in water, the formula used will be refractive index of lens upon refractive index of surrounding medium minus 1, 1 upon R1 minus 1 upon R2. Now first you will write the formula for the lens to be immersed in water. So in water, the focal length given is 80 centimeter. This one. Refractive index of lens you need to calculate. Refractive index of surrounding medium they have given 4/3. And R1, see, it is plane surface. So R1 is infinite and the curved surface has a radius of curvature 10 centimeter. Since we used to drop the incident ray from left and the radius of curvature of this surface, we will measure it moving towards left. So the rays will incident and will move towards right, and the radius of curvature will be measured by going towards left. Therefore, the radius of curvature is -10. Calculation, simple calculation, and you will get refractive index of lens equal to 3/2. Now this is question from 2007. A plano-convex lens, refractive index 1.5, has a focal length 10 centimeter. Calculate radius of curvature of the curved surface. This is the first part. If identical plano-convex lens is placed in contact with this first lens and the plane surface of the second lens is facing plane surface of this lens, then what will be power of the combination? So let us come to first question, that radius of curvature of the curved surface. So first write lens maker's formula for this lens and substitute the values of different quantities in the formula. 1 upon f is refractive index of glass upon refractive index of surrounding medium minus 1 into 1 upon R1 minus 1 upon R2. This is the formula. And when you will substitute R1 as infinite, R2 as simply R, refractive index as 1.5, refractive index of surrounding medium as 1, and focal length 10 centimeter, then substituting the values 1 upon 10 is equal to refractive index of glass minus refractive index of surrounding medium divided by refractive index of surrounding medium, which is 1, and 1 upon R1 minus 1 upon R2, and this will give you simply this expression. And calculation will provide you the value of R equal to 0.5 centimeter. Now second part is saying that another same plano-convex lens is placed with this convex lens, plano-convex lens, in such a way that plane surface of both the lenses are facing each other. Then find the focal length of the combination. So focal length of combination is calculated using the formula 1 upon f1 plus 1 upon f2. That is, power of the combination is equal to power of the first lens plus power of the second lens. Here power or focal length will be substituted with the sign. So both the lenses are having focal length 10 centimeter because both the lenses are identical, and both the lenses are having plus 10 centimeter as their focal length. So substituting the focal lengths and the calculation, which is simple one, the focal length of the combination is 5 centimeter or 0.05 meter, and hence power is 1 upon f, that is 20 diopter. Here you need to always remember that if single lens, convex lens, is cut in this line, both the lens will have focal length double the focal length of the single lens. So here it is just reverse process. Here two different lenses which are identical, when joined, becomes a convex lens by convex lens. So if single lens is having focal length 10 centimeter, then combination will have focal length just half, that is 5 centimeter. Now see, in 2009 the question is a thin convex lens has refractive index 1.5, focal length is 20 centimeter. It is completely immersed in a liquid which is having refractive index 1.75. Find new focal length. Again write the main formula. Now here there are two cases. In one case the lens is in air, in second case the lens is in liquid. So first we will write the formula for the lens when it is placed in air. Then substitute the values. 1 upon focal length in air is equal to refractive index of glass minus 1, 1 upon R1 minus 1 upon R2, where R1, R2 are not given, so we will not touch it, we will leave it as it is. Then divide the page in two parts, side by side. The second case also will be written. I divided the page. This will be the best way to represent your answer. For 1 upon focal length of the lens when it is placed in liquid is refractive index of lens divided by refractive index of surrounding medium minus 1, 1 upon R1 minus 1 upon R2. Substitute the values 1.5, 1.75. Leave 1 upon R1 minus 1 upon R2 as it is, because we are going to get the value of this term from here. And it is simply 1 upon 20 into 0.5, which is 1 upon 10. Substitute this value of this term here. So 1 upon focal length of lens in liquid is equal to 1.5 minus 1.75 divided by 1.75 into 1 upon 10. Simple calculation, and we will get focal length of convex lens when it is placed in the liquid as minus 70 centimeter. So conclusion is that whenever a lens is placed in a liquid which is having refractive index more than refractive index of lens, the nature of lens will be changed and focal length will also be increased. In 2005, the next question is that sunglasses have curved surfaces. Both the surfaces are curved, yet their power is 0. We know that sunglasses do not have any power. So reason is being asked in 2005. Write the formula for the lens. Then check out the curved surface have radius of curvature same. So when we are going to substitute the value of R1 and R2 equal to R, the R1 will have plus R value as we will move in the direction of incident ray, as the incident ray is always incident on the lens from left towards right. And the next radius of curvature will be same, that is R with plus sign. When we will substitute this value, 1 upon R minus 1 upon R will get cancelled and 1 upon F will be equal to 0, that is power will be equal to 0. So this is answer of this question. The way I am writing the solution, you are supposed to write the same way if you want to get full marks in your physics paper. So observe the way in which I am representing the numericals. In 2016 question is that show how focal length of glass lens changes when refractive index of glass is 1.5 and it is completely immersed in water with this refractive index and in liquid which is having refractive index more than glass. We know this answer because just before this question we have already solved this type of question, but the method is write the formula for lens to be in air, write the formula for lens to be in liquid as we have already discussed, substitute one by one the values in both the formula and divide the equation 1 with equation 2. You will find that this is common in both the expressions, so it will get cancelled. This term divided by this term on the right side, and on the left side focal length of lens in liquid divided by focal length of lens in air. Now we are ready to substitute the values. In first case, when refractive index of liquid is 1.33, substitute the values and you will get the focal length of lens 3.9, approximately 4 times the focal length of lens in air. So it is always better that you learn this formula, that focal length of lens in liquid divided by focal length of lens in air is equal to refractive index of glass minus refractive index of air upon refractive index of glass minus refractive index of liquid into refractive index of liquid. If you remember this formula, you can use it directly in this type of question. And we find that in water, focal length of the lens increases 4 times. It becomes 4 times the focal length of lens in air. On parallel side, we will calculate focal length of lens in liquid which is having refractive index more than refractive index of glass. So, focal length of lens in liquid divided by focal length of lens in air is refractive index of glass minus refractive index of air divided by refractive index of glass minus refractive index of liquid into refractive index of liquid. Automatically, the focal length will be increased and it will become approximately 5.5 times focal length of lens in air. But whenever lens is immersed in a liquid whose refractive index is more than refractive index of the lens itself, material of the lens, then lens will always change its nature. A convex lens will start behaving as concave lens, that is the diverging system, and the concave lens will start behaving as convex lens, that is converging system. So here these 2 points we will note it down, that whenever the lens is immersed in some medium which is having refractive index more than air, the focal length will always increase in both the cases. But the nature of lens will remain same if refractive index of surrounding medium is less than refractive index of glass. But nature of lens will change if refractive index of surrounding medium is greater than refractive index of lens. You can compare that the way questions are being asked in board in different years, they are having the same concept used again and again. Like here in 2000, they are asking relation between refractive index of surrounding medium, refractive index of lens in these 2 cases. Now we know that if there is no refraction, the rays are moving straight without refraction. That means there is no difference in the refractive index of the 2. So N1 is equal to N. But here convex lens is changing its nature and diverging the rays. So definitely N2 is greater than N. So N1 is equal to N and both of them are less than n2. Now after 5 years, see, the same type of question is repeated. Here they are saying draw path of refracted ray when parallel beam incident on concave lens. Refractive index of concave lens is n and lens is immersed in liquid of refractive index n1, where in first case n1 is greater than n, second case n1 is less than n, and third case n1 is equal to n. So we know that when n1 is greater than n, the lens will change its nature. Focal length will increase and concave lens will start behaving as a converging lens. When n1 is less than n, focal length will increase, but the lens will behave as its normal nature and it will diverge the rays. And when the refractive index of the two are same, there will be no refraction shown by the incident ray and they will move straight. As they are coming parallel to each other from infinity, without deviation they will go straight. 2019, the simple question, find focal length of convex lens whose radius of curvature of the two surfaces is given this and refractive index is this. Simple application of lens maker's formula. Write lens maker's formula. First step, substitute the values with the sign. Second step. So substitute the refractive index of glass R1 plus 10, R2 minus 15. And now simply solve it and you will find focal length as 12 centimeter with a plus sign. Interestingly, in 2018, the same question with different values being asked. Here, focal length you need to find R1 is 20 and R2 is 30 by convex lens, refractive index of glass same as 1.5. So, you can easily solve and practice this type of question, and I hope that you get such a simple question in your semester 2 exam also. Again, the question which we have done earlier also, 2004, same repetition of the same concept used in this question also, that the equiconvex lens whose focal length is 100 centimeter when this lens is placed in water. Calculate focal length of same lens in air. Now in the previous questions we have seen the focal length in air is given and we need to calculate focal length when it is immersed in liquid. Here focal length in liquid is given and we need to calculate the focal length of lens in air. Formula: focal length of lens upon focal length of lens in liquid upon focal length of lens in air, refractive index of glass minus 1 upon refractive index of glass minus refractive index of liquid into refractive index of liquid. We have seen and we understand that this formula is very important, and if we remember it then we can save our time. Substitute the values. The focal length of lens in liquid is 100, glass refractive index 3 by 2, liquid's refractive index 4 by 3, here also 4 by 3, simple calculation and you will get focal length of the lens in air as plus 25 centimeter. Now this question is also repeating its concept we have already discussed. When a lens is cut along AV, then the two parts will have focal length just double the focal length of this lens. Here we just need to show it because they are asking what will be effect on the focal length of this lens if it is cut along AB and if it is cut along CD, which will be perpendicular to AB. So first part of the lens and second part of the lens, we will calculate the focal length of the two parts independently and will show that this is having focal length double of the focal length of this lens. Focal length of this lens is 20. So focal length of this part and this part will be 40 centimeter. So divide the page, write the main formula, and for the first half of the lens, you can see that R1 is plus R and R2 is infinite. Substitute the value and you will get refractive index of glass minus 1 upon R. That is, if whole lens is considered, then focal length of the whole lens is refractive index of glass minus 1 upon R1, which is plus R, and minus 1 upon R2, which will be minus R, and this will add and will give you 2 by R. So just compare the focal length expression for whole lens and for the half part, and you can see that this value is nothing but 1 upon 2f. So 1 upon the first part focal length is equal to 1 upon 2f. Therefore, focal length of first part is just double the focal length of lens. Similarly, in the second part, we can write R1 as infinity and R2 equal to minus R, because we will move towards left when we are going to measure the radius of curvature of this surface. While in practice, we always incident the ray from left to right. So whatever distance is measured opposite to incident ray, that will be with negative sign. So writing formula and substituting the value, you can see that the second part is also having the focal length. This part is equal to 1 upon 2f. F is focal length of whole lens. F2 is focal length of second part, the second half of the lens. And F2 is also equal to 2f. So we have already discussed that if a biconvex lens is cut into equal halves along the vertical line AB, each part will have focal length just double the focal length of the convex lens. And interestingly, if you place these two parts in any orientation, the combination of the two will have always the focal length of the main convex lens, which is f. In the same question, they are also asking that if lens is cut along CD, CD is passing from the center of the lens and it is perpendicular to AB, then what will be focal length of the new part, the two parts? So here, the lens is having focal length unchanged. The only thing is that since every point is having complete image of the object, so if half lens is used, the half rays are passing and forming image, so intensity of the image will reduce, brightness of the image will reduce, but there will be no change in the focal length of the lens and position of the image. In 2001, again same concept is used. Here lens is made of two materials of refractive index N1 and N2. The question is that if a point object is placed at the principal axis, what will be the position of image and how many images we are going to get. Since focal length depends upon refractive index of material of the lens, so as there are two refractive index material used, so there will be two focal length of the lens, and hence the rays will be converged at two different positions by the two different parts. So we will have two images of the same object because the lens is having different focal length. For N1 it is F1, for N2 it is F2. So this is the first part of all the important questions which have been asked in previous years from ray optics chapter refraction through spherical surface. In the second part, we will conclude it with the magnifications question, magnification of lens question based on this part, and combination of lens with other lens, combination of lens with other mirrors. All the questions are asked in some of the previous year paper. So this whole discussion is very important and will give you the way next, that is this year, question can be asked. All my semester 2 exam topics are compiled in same playlist, which is semester 2 exam class 12 ISC, and you can go and find all the topics, quick revision, important questions for your semester 2 exam.